Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. There we go. Sorry for the slightly late start. I had long pings, and I guess my machine needed a reboot. So that's fixed. And I guess we're ready to get started. I wasn't able to stream last week. I was just super brain dead. And I almost didn't stream this week for the same reason. I've been pair programming at work all day for 4 days straight, which has been really productive. But makes me a little loopy by the end of the day to both code and communicate for long periods of time. So I might be a little less talkative today, but should still be fun. In the last 2 weeks, made a bunch of progress in the xenowing. SKTS is productive for whom? For my company? I don't know. If you're asking who my company is, that's GraphCore. So in the last 2 weeks, I did a lot. I mostly have been working on this thing which I call Buster. Let me pull up the diagram again. And Buster is sort of this reusable bus component thing that I was working on. Here we go. And the idea is that it would have multiple primaries and multiple replicas, and you'd be able to specify how much you want of each, and things like the data path bit width, and it would handle a little bit of memory mapping for you. It would handle all of the arbitration to give certain primaries priority over the other ones, and also make sure that when data comes back from replicas, if reads are issued, that all of that data gets back to the proper primary. So pretty cool stuff. It ended up being a lot of work, long story short, and a lot of testing. And I don't really feel like I tested it as thoroughly as I quite want to, but to be honest, I got really bored of that. Like once everything started working, I think it was not this weekend, but last weekend. Maybe it was. I actually don't remember. But once I started getting things working and things kept working in tests, yeah, I got pretty bored. So I thought, why don't I just actually try to hook everything up? And that turned out to be a good idea. Let's see. If I go in my xenowing shell here, I think I can do make Buster test. This actually might not work because of the branch that I'm on, which I'll get to. Maybe I just might stash everything, actually. Yeah, that's got a few things going on in here. Let's do that. Let's stash stuff. And I'll get to the Verilog generation stuff that I'm working on today. By the way, hi guys in the chat. SKTS, Dark Second, Chief Detector, and Zhao. How's it going? And I didn't catch who it was, but I think someone else said hi before I had to restart the stream. So sorry I didn't mention you. I don't see the chat from before I did that. If I missed someone. Or maybe that was Chief Detector. I don't know. Zokwar, that's who it was. How's it going? So anyway, this ran actually fairly quickly, all these tests on Buster, and I literally just test some specific configurations and some specific tests, like a single read through replica 0, single writes, and then read all, so read a bunch of addresses between a given primary and a given replica. And I wanted to make this kind of fuzzing test, which I think I'll still do eventually, where I have this sort of 4 primary, 4 replica thing, and it'll just kind of randomize the traffic between them. To some kind of pattern to which the results of all that traffic should be deterministic, and then actually push all the traffic through it and then make sure everything matches. That's kind of the idea. But I haven't gotten around to doing that. And at some point, I might even look into some formal stuff for this kind of thing, which I think would be really appropriate. But I don't really have my head wrapped around that stuff very much, so I want to kind of continue on the design. Anyway, I ended up doing sim and xenowing now. And if I do cargo run. I'll do it in release because otherwise it's really slow. I need to give it a ROM file, which is going to be in rom.bin. And this will build. And this builds a simulation of the full xenowing, or at least as much of the xenowing as exists right now. And you can see here, this is code from the ROMs. It says xenowing online, and this would be over UART, but right now I just have that dumping to the screen. Then get ready for some fade babe. It's some total cycles where it used to put a box on the screen, like software render a box into the frame buffer, and then that was displayed when I had the old board, but I still haven't looked into HDMI output for the new board. While getting all this bootstrapped again. But anyway, it does work. This is the ROM, and it goes through the memory mapping stuff. Everything is made with these Buster modules in this sort of hierarchy, which is really cool. So this is kind of coming together. And I'm really happy about that. And what I'm doing now is the way I hooked up like the UART and everything, if I can show some of this, is actually the xenowing itself. If we look at some RTL and kaze. It's really verbose right now because I just kind of did some copy paste stuff to hook up all these different buses. But I mean, obviously this stuff could just fit in a function. So give it some source and some dest, and then some names of these, and then it would just be able to do this. So I'll refactor later, but I wanted to see what it would look like this first. So anyway, this is the xenowing. It consists of Marv, which is the CPU, and then this Marv interconnect bridge, which is kind of this 32-bit bus to 128-bit bus bridge that hooks up to the rest of the system, and then the rest of the system is contained in this interconnect. And the interconnect module also has a bunch of verbose stuff that I need to refactor, but it mostly just stacks together some busters. So there's one for the CPU, and there's one that I call sys. And this follows a diagram that I also made that I think I've shown several times, but I'll show it again anyway. Here. So this is going to be the topology of the whole system eventually, but a bunch of stuff is grayed out, and what remains is what I have. So the Marv talks through this bridge, and then it connects to the interconnect, and all of this is sort of contained within the interconnect. Right now, it's only this sys module and this, or CPU module and this sys module. And then this sys module actually fans out different ports for the BIOS ROM LED interface and UART interface. And then this CPU one also has a port for this DDR3 interface. Now this line's dotted because eventually this connection won't actually be here. That's kind of what that's supposed to mean. So the gray stuff is stuff that I'm going to do later. I figured I could just progressively update this document as I do it and kind of use this as a design document. And then I'll get rid of this dotted line. So, but right now, all this interconnect stuff is these two modules. And then, the interconnect module exposes a port to connect to this bridge. And then it also exposes these three ports and this port. Yeah, I know it's not as fun as MS Paint, but it's a lot easier for me to deal with. Now I can move things around and the arrows follow. That's refreshing. Anyway, so that's really all this interconnect does is it instantiates these two Buster modules and then hooks up all their ports. There's a lot of parameters to Buster, which I might refactor how that's specified, but it's things like I think it's one primary and two replicas in this case, and then there's 28 address bits, 4 of which are going to be used to select the different replicas. And I stuck with 4 here, which is way more than I need, because with that you can have up to 16 replicas for a given Buster instance. And I don't think this will ever get that high under the sys one, and the CPU one I think will only ever have 2. But it's still easier to just use a full 4 bits for that because of the way it makes the address, the memory map look. So if I go into doc, I think I updated all of that as well. Had a busy weekend. Now the memory map has changed, so now program ROM is from 0 hex to where that ends, and then the system regs are this is from wherever this is. And so the point about using 4 bits is that it's these 4 bits that represent this single digit that is used to select the output of that Buster module, whereas the CPU one also uses these very top 4 bits. So these top 4 are the CPU bus ones, and then these 4 after that are the sysbus ones. When this is when this is 0, I think. And then, yeah, when it's 1, we go to the RAM. But I could also have more, but again, it makes the memory map really clean to have it organized this way and just use 4 bits every time, because then it represents a whole digit. That's really my whole point here. And the other thing is that now that all of this is connected to a 128-bit bus, which the whole reason I'm doing that is because the DDR3 interface is 128 bits wide, and eventually I want to be able to DMA from here into like some local memory that'll be on, for example, this color thrust, which is the GPU, Wideboy, which is the current name for the SIMD processor I want to make, which doesn't exist. Same with this audio unit. All these are going to have local memory, and I want to be able to DMA to and from those with the full 128-bit with data bus. So everything on here is connected to that 128-bit bus. And right now that includes the LED interface and also like the BIOS ROM. And that can be a little awkward when I have registers down here. So the CPU is doing 32-bit writes, and there might be a register down here that can basically be up to 32 bits. It's a bit awkward to, when implementing these, to kind of split up those additional addresses. In fact, I think because these are 128 bits, I guess you have the byte enables if you're doing like a write or read, but other than that, you don't really have any way of getting any of those lower address bits back down here. So I think what I'm going to do is also align all of the registers to 16-byte boundaries, and even if they're only like 1 to 4 bytes for the registers themselves. And so far, I think I did that with the LED interface and also this UART transmitter. So in hex, everything starts here. So this actually looks nice because then the whole memory map is going to be based on these like clean hex values, which I think is going to be really nice. And so far, it seems to be fine. Of course, it means that you throw away some of the address bits, but I think we have still quite a few to work with, and we're not going to end up with that many registers. So I think this all in all works out pretty well. And so far, again, it's running in sim. So pretty soon here, I want to get this running on the actual FPGA, but there's a lot to do still before we get there. I think the most important thing is actually generating Verilog from kaze, which I'm kind of starting amidst doing some other things. So there's still some more stuff I want to do in sim before that. In particular, I want to be able to get to the point where I'm reloading programs over the UART, and I want to implement all of that against the simulator, and then hopefully test that on the real hardware, which I think that's going to work. But to do that, I want to set up a proper, like, I think I had this program which I called Xenowing Blaster, and that was basically just watching the file system for changes to the ROM, and then it would upload that to the system. But for this time I'm implementing this, I think I actually want to have the UART receiver on the system be accessible from the program itself. So I'm actually going to split up the ROM into 2 parts. I'm going to have the BIOS, which I think I'm going to call it BIOS. I actually don't know about that, but I think that's appropriate. And the BIOS's whole job is just to contain like enough stuff to initialize enough of the system to a known state, and then also try to load a program, which it will do from the UART. And that will load it into a separate program ROM. So right now there's program ROM, but I'm also going to have, I guess I'll call it program RAM at that point. And so its whole job is to load that program, then jump into it, and then the program RAM will take care of everything else. Yeah, I could also call it kernel D, definitely. So I think that'll be really straightforward. But then what I want to do is I want to have interrupts that can come from the UART receiver, and then have some kind of command processor that's some kind of command processor that will do things based on those commands. So then what happens is if for example the host program is watching for file changes for the program, so I can rebuild that, not necessarily the ROM because that's going to be baked into the hardware, but the program itself, if it sees a change, it'll send a command that says that changed, and then the system will respond to that by just going into reset, calling back into the BIOS, and then the BIOS is just going to reset the system again and then load the program like it did when it started up. So I want to have all of that implemented in the simulator before I even test on the real hardware, because again, I actually expect things to basically just work once I get on the hardware, as long as I model things the right way. So in order to model that, I need to properly model the UART stuff in sim. And all of the UART stuff that I have from the previous iteration of the xenowing was, well, I think most of it was in Verilog, not quite all of it. So if we go in here, there's RTL old is where all that is. And then, yeah, I have a UART transmitter and this UART transmitter interface, which is going to go away. And then this UART clock divider. And then the receiver, I actually did port to the Python version of kaze, which I think is fine. So what I decided to do first is port this over. So take this Python one and then port it over to the Rust kaze. Now, I know I'm just blasting you guys with information here, but I'm kind of in a bit of a rabbit hole. So this actually is the Rust implementation of that, or the Rust port. And I ported it pretty much straight over. Actually, this is not quite the latest because I need to do a git stash pop. Like that. There we go. This is the latest. And it doesn't look as clean. I mean, I'm not going to give it like a full side-by-side comparison, but especially this conditional syntax was a bit lighter in the Python version, even though it relied on some nasty stuff. The Rust one, I think, looks uglier because of the way that everything has to be passed around in tuples, and there might be a better way to write the same state machine logic. That's the kind of abstraction that I want to look into a bit later. But for right now, it's not very pretty. But I thought, well, that's fine, because if I can make it work, I feel pretty happy about that. So I implemented this, and then I added in this RTL project, which is where all of the kaze code is. So like this, the CPU, for example. I decided to add a main.rs there too. So normally this RTL project here is used as a library. And there's all these sim projects that I have that will, like for example, the peak buffer, or for the FIFOs, or for the buster, all these sim projects, and then those use a build.rs script to include the RTL project and kaze, and then generate code, Rust simulator code, based on some certain configurations of the RTL. And then, of course, that gets generated, so we can actually look at one of these in one of these build directories. And then that makes this modules.rs, which has a bunch of simulator code, all generated by the compiler. And then we actually, in lib.rs there, we actually write a bunch of tests against that, which is just straight up Rust tests that stimulate one of these modules and then test what comes out. So pretty straightforward how all that fits together, I think. But then I also need a bunch of this RTL stuff to generate Verilog. So the way I think I'm going to do that is I'm just going to add a main.rs to the same RTL library, so that when you run it as a program, it's actually going to generate Verilog for a specific set of modules that we actually want to use. And then I have this Mimos A7, which is the name of the board that I have. And in that directory, right now there's some tests projects, and in here we have like a DDR3 test, which has all the Xilinx files and everything for that. And it's also organized so that there's like a IP directory and a MIS directory, which I might, like in this case, DDR3, there's a tool that can interact with the serial port and find out how many cycles it takes to do all the reads and writes and everything. And then also, same for the UART, there's this big stress test. But in addition to that, this is going to have the actual xenowing project for this board. And that's going to refer to the generated RTL from this program. So right now, if I do cargo run, and then I output that to, I think it's generated.sv. I think that just works at the moment. Yep, it does. And then if we look at this generated SV, which should be in here, we get the first Verilog output, which I got last night, that comes from kaze, which, again, it's this UART module, and it looks kind of ugly, as most generated code does. Here's some logic for registers and their next values. Here's the clock and reset handling for each of the registers, and then there's a bunch of nodes for temporaries, and then there's all this logic that just assigns these values to all these temporaries, and also these next register values, and also the output ports. So kind of straightforward, I think. the way that this works, and the compiler work for this has been really straightforward too. It mostly just matches the same stuff that I've been doing for generating simulator code, except it's even simpler because the internal, like the graph model that Kaze has internally was always designed to describe hardware, so it's pretty easy to generate Verilog from it. But when I actually ran this on the system, so I swapped out the old generated one, which was in this RTL old, because this also has this UART receiver, which is the old Python implementation. When I put that into this test project for my board, so we're going to test and UART, and now this UART project now refers to this new one, which was mostly just swapping it out, but then I also had to add these synchronization flip-flops because after another rabbit hole here, but the old UART receiver did this synchronization chain of flip-flops to synchronize the input receiver, like the RX signal, into our clock domain. And I described that register chain in Kaze before, but now I do it here just to make sure all of these registers get this async reg is true attribute. So I think I might actually add a synchronizer chain construct to Kaze, which would output registers that have this thing in it, because I think this is going to be pretty common. But anyway, I did it by hand here just to hook this up initially. And that's pretty much the only difference. The rest just instantiates the module, and then the rest of the interface is the same. So unfortunately this doesn't work, and I don't know why yet. So we got to debug that. And I think there's several ways we could debug it. But I think we're not really going to get around actually writing tests. I had thought that this would be a good place to start with a code gen because I already had this test project. So I thought that I would write the receiver and then plug it into this little test harness. And then if that worked, then we knew we had a working receiver. And then I was going to just sort of slowly replace the transmitter and everything sort of within that framework. Because also, if you have a receiver, then a good way to test a transmitter is to hook it up to the receiver and just like round trip a bunch of data through it. So I thought I could do that relatively easily in Sim. And then maybe I could skip the simulator test for the UART receiver. It seems that was a bad idea, and that I'm going to need to do these tests anyway, which I'm pretty okay with because like, if worst case, I'm just going to test this more, then maybe that'll help us find some other bugs anyway. So, long story short, Verilog Gen is starting to work, but I don't dare commit any of it because this first test module that I tried doesn't work. There's a bug in here somewhere. And I've looked at the port for this receiver, like the Kaze code for it, which I think was in here, versus the Python one, and for life of me, I cannot find what the issue is, just looking at these two and comparing them. And I think testing's the only way to go at this point. So that's what we're going to do. A lot of words. But yeah, I'm feeling good. Like, there's a lot of progress, and I think it's going to be really nice because once we get all of this working, whoops, something's wrong with my sound card, it seems. I gotta fix my music here, otherwise I can't work. Okay, I need to be right back for a second here. And I think I'm back. Is this the right mic? Do I sound the same? I should sound the same. There we go. Yeah, not so talkative indeed. So classic. All right, thanks. So yeah, I'll fix my music and then I'll get started here. But yeah, this is one of those things where I thought I could get away with maybe just kind of using the other test stuff I had as good enough tests, but worst case, we have to test this thing in isolation, which so far has been a really good thing to do for all the modules in this project. So I don't really mind doing that yet again. But I thought I could save some time, but as it turns out, I should actually test this anyway. So that's what I think we're going to do now. So in this sim directory, this is where I put all these test projects. And again, you go in sim, We can do cargo new -- lib, and we can do uart. And we'll use this as a catch-all project for all the uart test stuff. So just like all these other ones, I'm just going to copy some stuff here because I'm lazy. So this has some dependencies. Now, actually, there is one thing that kind of sucks here, and that's currently, because I develop everything against this sort of published kaze, and the kaze I'm running with right now that does this Verilog output is not published because it has a bunch of Verilog gen stuff. We're going to have to not use this for a while. But that's fine. We can actually just leave that as is and just not refer to that in this RTL project. Yeah, if this is kaze, I think 0.1 is one. Yeah, that's actually right above there. We'll do that. Then I think we can build stuff. So yeah, I'll just go into this other sim and pull the build script from there and the cargo and everything. Yeah, great. So now we can do uart. I think I do generate rx. So I have this set up. I'm actually going to close a bunch of these tabs. Whoops. Did I just close the one that was modified? Probably. Yeah, that works enough. Yes, generate rx, and then I give it a clock frequency and then a baud rate because it will figure out when to sample different signals based on those. And so I think, I also know that the receiver is going to sample it 4 times whatever the baud rate is. So if I do something like 16 hertz is the clock frequency, and then it's 1 baud, that means there should be 1 bit every 16 clocks. And then everything in here should work out. Yeah, this tick rate is the baud rate, which is 1 times 4, and that takes clock frequency divided by that. I could also, just to make tests easier, I could do something like 4 and 1, which I might actually do. I think that's kind of cheeky. Yeah, I might do that. At least for initial tests, I think this makes some sense. And then we're going to actually need to write some tests. And I'll just copy some of this. Easy. So this, I'll make this uart rx module. And do to do. So now if I go in here, I should be able to do cargo test. And I'm in the wrong directory. Cargo test in uart. There we go. And, oh yeah, not peak buffer. This should be uart. Cool. So we're going to reset this and we're going to do m.rx. So I think I mentioned this before, but one of the really downsides of the way I have kaze right now is I don't have any way to like bundle signals and present the different ports of the module at the top. So normally in Verilog, let's see, like here, you have all the input and output ports at the top, and you're kind of restricted to doing that. I think I actually might make that a pattern in kaze as well, because it's really helpful to see what the interface of the module is before you see all the implementation details. So what I've been doing is kind of cheating, and I go into these generated Rust simulator folders in these target directories, and I actually look at the inputs and outputs in the generated sim code, which is, I think, kind of cheeky, but it does show me exactly what I need to provide for this. So if we say m.rx is true, because we're doing uart here, That's what we want. So I actually am going to look up UART protocol on the Google. And we're just going to straight up use someone's diagram here. Just trying to find a good one because there's a lot of ways to show this. And I think this one looks good. No, because I want one without the parity bit, which we don't use because we don't need it. Although it doesn't really matter. It's optional. So yeah, I'll actually bring up this picture, even though it has some extra stuff that we will ignore. So yeah, so this is UART. So this is a transmission for a single byte. So the idea is that we're doing a UART receiver here, so we're only going to look at how to receive this, but this shows enough for the protocol. So every byte, normally the line, if you're going to send over UART, you have a sender and a receiver, and then one line. And the sort of idle state and the initial state is that line is held high. And when you're ready to start stuff, you transition this to be low. And so at some kind of data rate, which in this case is specified by the baud rate, we sort of have one transition for each one of those ticks at that rate. And so in this case, we're going to start with it being high, and then we pull it low for a full length of one of those ticks. And that's the start bit, and that's how we indicate to the receiver that we're going to send some data. And then we have 8 bits worth of data. And yeah, you can see it sends the lowest to the highest. And then after those 8 bits, we have an optional parity bit, which we don't use right now, so we'll ignore that. And then there's a stop bit, which is where the line is held high again for the duration of one of these clocks. So the idea is you hold it low for a full duration, and then you have one duration for every 8 bit, each of the 8 bits where this line is either high or low depending on the value of that bit, and the receiver will know to sample because it's agreed upon beforehand what the rate of this actually is. So when the receiver detects it, it's going to sample at the middle of all those areas to see what the actual values of the bits are, and then finally it's going to sample this stop bit, and that's how it's going to know that it's basically done. And so our receiver does basically the same thing. I won't go over the logic in too much detail of how you do this, but what it does is it runs its ticks at 4 times the actual rate of this, and that way it's able to count out to where the middle of these should be relatively easily without missing one of these start bits or getting too far out of skew, because you will actually not be in perfect alignment with the sender most of the time, and that's fine. You just have to be able to make your receiver robust to that. And again, the Python implementation I had of this worked very well. I had that running for hours and hours and hours, and it never found any issues. So I'm pretty happy with that, and I trust that quite a bit, because even though you can test things for hours and there still might be a bug in there, but this stuff is pretty simple, so I kind of trust it. And also the data rate is relatively slow, so I wouldn't worry too much about that as long as we can get it working. But I have no idea what went wrong when I ported it to Rust, so probably some stupid mistake, but who knows. So what I want to do is, since we're testing the receiver, I want to send it some dummy data, which I'm going to do just by wiggling this RX line in a test. So again, I made this, 4 hertz, and then sort of one transition every 4 cycles, and that's going to be important. So we want to describe this. So let's just do like some single thing. Name me a better name. I'll call this to-do. Again, I should be able to run cargo tests, and this should basically do nothing. And it warns me about the name, which is great. That's what I wanted to do. So we set Rx to true for the start state, and then we propagate that. And then I think right away I want to start a transaction. So I think we'll just do this. We'll wait a clock or two, and then we'll say start bit. So m.rx is false. We'll propagate that, and then we need to wait 4 clocks, right? I think we just do that. I don't know actually if we want to change this before this last one. So here's another problem that I will point out with kaze is that I actually would love to be able to generate these simulator traces so we could actually see this a bit better and see what the module actually does. That I think is a planned feature at this point, because it would make this really easy. Yeah, sometimes it's hard to get all these counters right. But I have a feeling we'll get this to work. I'm just not entirely sure if I want 4 ticks here. But I think I do. Yeah, we'll see. We'll just have to see. Anyway, then we'll start doing data bits. So we can say let data is 0xAA, for example. And then we can do for bit index in 08. Let bit is, and we send again, we send the lowest one first. So we can do data, shift right, bit index, and 1. And I think we'll do is not equal to 0, and that way we can say m.rx is bit. In fact, we'll just do the whole thing here. That's fine. M.prop. I think we need to propagate between all these as well. In fact, I think I'll factor it this way. And there's going to be a stop bit where we say m.rx is true. Bring that high. And then we do while not m.data ready, I think is what I called that. Yeah, data ready. I think I might change that to data valid. Then we'll do m.prop. Like that. So we basically put this down to true. And then we're going to wait until the data is ready. Which I think in my implementation happens in the middle of this last bit, which is fine. I think as soon as it samples the stop bit, then it's done. And then eventually we should do assert eq m.data data. So that seems like a decent test to start out with. And it passed. That's annoying. I mean, great that it worked, right? But why didn't it work in the actual system? That's a bit concerning. Yeah, it probably does need some proper tests. Just to check here, I'm going to set this as something not correct, and it should catch that, and it does. So, I mean, it means data got through this. But yeah, we can do, let's do this. Let's do single byte. That's great that this worked. But again, didn't work in the real deal, so no idea why. It might also be that I hooked it up wrong, which I actually want to take a second to look at, because that'd be kind of funny, I guess. Okay, apparently I changed one of these diagrams. Yeah, this is the only difference. It actually uses a different module, and then of course the project needed to point at a different generated.sv file. And again, instead of feeding Rx directly, the sync chain is out here. So these, we take the last sync chain value bit, and then the sync chain is here. And on reset, I think I put all those bits to high, which again is sort of the default value. Wait a minute. This sync chain looks wrong to me. Wait a minute, because I use this here too. Yeah, this is wrong, isn't it? This should be this down to 1, shouldn't it? So the way this works is I have this chain here where you give it a number of stages. In this case, it's 2. So you can basically read this as 1 down to 0. And initially, we set all those, in this case, to 0, because this is a reset thing. So this is supposed to be 0, and then we're going to feed 1s into it. And the way this works is I say stage is -1 all the way down to 0. So the next value for the whole chain, in this case, is all 0s. In fact, I should be able to do that, I think. Oh no, Artemis. That sounds terrible. But yeah, so we set all these to 0, and then we sort of use, we basically treat this as a shift register. So if it's reset, we reset the whole thing. And otherwise, it also looks like I started in this end else begin another line, so I might actually change that in the Verilog output of kaze. But anyway, so it looks like I shift in 1s onto the bottom. The way I had this before, it did 2 down to 1, and then put this at the end. Or 2 down to 0. Maybe this was correct, actually, because... Yeah, I think this actually was correct. Because we take everything except this top bit, which we discard. And then essentially shift that left by putting a 1 bit down at the bottom. So I think this actually did look correct, which is what this one was doing too. Yeah, that looks good. And then the output is the top stage there. So I think actually that does look pretty good. And then this is basically going to do the same thing. I think we can get rid of that. Again, we have sync stages. And we reset those all to 1. The idea being that at reset, this should be high. And then we pull in bits from Rx here. Every cycle by discarding the top bit, taking all the rest of them and adding this at the bottom. And then we take the very top one, the new top one, or I guess the current top one is more accurate. And that's the value that we output out of this chain. This seems correct to me after going through it again. And I don't really hook it up any other way. Cheesy, how's it going? So yeah, I think this looks good, which is annoying because it doesn't work on the hardware, that is. So what I will probably do is make some kind of fuzzer test. I actually I don't have chip scope set up. I don't know if that's actually available in the free version of the Xilinx tools. Is it? Or was it a cable I was missing? I actually don't remember. Because that would be a great way to look at this. Yeah, let's just say I don't right now. But that would be a great way to debug this, and I guess the ideal way. But since I don't have that hooked up or set up or whatever, we're going to have to try and fix this in Sim. Which is annoying because I was hoping this would find a bug at least. Especially because this right here is maybe not the best way to set this up with 4 and 1 like this, because we actually want to have, like, I do want to make it some kind of integer number of clocks here, just to make it easy to simulate sending. I'm going to increase this. So let's say it's a 16 hertz clock with a baud rate of 4. And then these should all be 16. And things should still work. We'll just try that really quick. And now it actually hangs. So we may have already found the bug here. Is that correct to do it that way? I mean, it must have been, right? Yeah, I think we might have just found the bug. I hope. So I'm thinking a bit here because it'd be nice to have like a VCD output to try and debug this with, which stands for value change dump. And that's a really standardized format. Date, version, comment, all that stuff. Then we have all these variables that all end up being mapped to like ASCII characters. And then there's this dump vars thing where it outputs changes to all these different variables, which is, I think, a really ugly format. But it's also super standard, so we could look at this in like GTK wave. But I'm actually considering hacking together just to test this. What if we dump some wavedrom output instead? Which I believe I mentioned before. It's this timing diagram generator thing. And it's this JSON format, which I think might be a bit nicer. But obviously these are a lot smaller. And the other thing is I would just hack together output anyway, but I think if I'm going to hack something together for now, which I kind of want to do as like a prototype while trying to test this, I might as well go with this easier format if it doesn't really matter. I think I'm going to do that. I think I want to do that. Where do I start? Let's do a couple things. I'm actually gonna... Well, can I just do it in this test? Is it no capture? -- no capture. And I think this would allow us to do, for example, print line. Yeah, and then we see it there. So I might actually hack that in the test here. Let's see if we can get output here. I think that seems like a fun idea, to be honest. And I think I'm also going to go back to what we had before, which worked, so we can kind of see what's going on here. And again, now this should pass, which it does. And I think I might do this too. We'll wait like 1,000 cycles. And what we can do is if m.data ready, we can break. And then we can assert data ready is true and that the data is what we wanted. The reason I'm doing this is so it will always terminate. So if we go back to this, where it didn't work, this will still terminate and now it will fail. And let's do the data check first so that when it fails we see, well actually that doesn't really matter. It's going to fail anyway. But I'm thinking what we can do now is make some kind of dump and then output it before we do the assertions. So let's hack this together in the test, then we can figure out how. Then I can just kind of stash it away somewhere in a gist or something and figure out how I want to do this properly if I want to do that later. I think that sounds fun. So to do that, we need some state. So let's do, let's see. Let mute signals is, I don't know what we'll use for this. Can do nested collections hash map. Let's actually do a B tree map so we get some kind of deterministic ordering of the output signals. Let's even just do it this way. We'll do struct trace, and it can have a B-tree map from the name of the signal to values. Which, if we wanted to be real cheeky here, yeah, I guess there are some limitations to this format because I think you can only go up to like 9 values here. Or no, these are just colors, aren't they? So we would just have all the data out here. No, we can make this work. This is good. So then what I want to do actually is I can just do this with a vec of chars. Is that enough? I guess we'd still want the actual data, so that's not really enough. Okay, so we'll do struct trace signal. This can be a trace signal. And we can do wave, and this will just match the output format. This can be a vec of char. And actually we could do, let's do data, and that'll be a vector of a tuple where we have char. No, actually I do want parallel arrays here. Because we might not output data if we don't have to. Right. So the data actually is going to be a vec of string if we output it this way. Again, to match the output format. And this I like, because then you have the name here, and then the wave and data here. And then we'll do some stuff. So we'll do impl trace function new. And we'll just do signals. And I guess we can give this a writer. And we'll do use std io result and write. Oh yeah, and this needs to be w write to make this generic, and then this is w, that's what we want. Okay, and then in here we can do something really basic like write line. Again, we're just gonna kind of hack this, so we'll do w and then signal like this, and we'll end like this. And I think because these are format strings, we need to do this here, and I think we need to do the same here to escape those braces. And then we can do for signal in signals. And actually, this will be name signal. In self does signals, hot signals in your area. Then we can do right. Oh, you guys, why do you watch this crap? I think we're actually able to have a comma here, even though normal JSON doesn't. But then we can do name. And then we can do, is there single quotes, which makes this even easier. And we'll have the name there. And then the wave is this, where we need to flatten that too. So we'll make variables to do that. And then data. So let wave is going to be, we can just output all the values. In fact, wave that I had here was already a string, wasn't it? No, it was a vector of chars. So what's the easiest way to do that? You know, it's actually probably easier if we just split this up. If we do this, for example. You didn't see Adam since a moment before the stream? Don't know what you mean. Oh, the editor. Yeah, this is Sublime. I do need to switch, though, to VS Code, I'll admit. In signal.wave. And then we can just write all the chars individually, because who cares? And all these, by the way, need to propagate this error state. So let's do that now, even though the compiler's going to tell me to do that later. And then, yeah, so now here we finish off the wave and output the data. In data, it's a vector of strings, actually. So let's just do the same thing here. Be cheeky. Or actually, does it work if I have an extra space at the end of that? Seems to. That makes it easy. Because then what we can do is for s in signal.data, we can do write w, and we'll do this with a space there. We write out s. Christ, extended graphing clusters, totally. Oopsie doopsie. No worries, man. No worries. Right, so now I think here we can do let mute trace is trace new. I think you could name the signal that, but you couldn't output a lot of stuff here. Oh, yeah, I need to make this mutable so that write can take it. And do I iter here? Yep, and I iter here and here too. I think also I could take a reference to these, but I'm in the habit of using .iter instead. I don't know what's recommended these days. Been using Rust for a long time and have not bothered to keep up with with those kind of things. But now we have the trace, and then at the end we can do trace.dump, and let's just do stood out. I guess in the middle. And this will probably just dump out crap because we never actually populated any of that, but it does look correct. So that's fun. And then we actually need to output all of these. So I think what I want to do is make a little function here, which I can just call t. Update trace. Sure. T is trace. And we'll give it the module. So M is this. And maybe it works to close over this. I don't think it does. Anyway, we'll do this. We'll do t dot, I mean, it's all the signals, which there are only 2 external ones right now. Ultimately, we'll want to generate something like this, but for now, we can just take all the outputs, which again are data and data ready. And I might add some debug outputs just for debugging this. But then it's, let's see. I'll not worry about the types. I'll just kind of do it this way. Also, does it work if I specify? I'm just in the little editor here specifying some additional stuff, but I think it, yeah, it just ignores that if it doesn't apply, which is great. Then our code will work. So then we need to do t dot signals dot entry, and then we'll do some string dot into, and this string will be the name of these. So in this case, we need data. Dot or insert, and this will be trace, a new trace signal. So we'll do impl trace signal, function new. This will be wave is vec new and data is vec new. And so we don't just create a ton of these. We can do or insert with, do this, and then we do trace signal new. So we can do even let data as this. Okay, and then we do data dot wave dot push. And this will just be the data. So I think we just do 3 in this case. And then we do data dot push. And this will be the string. And so here we could do format. And we'll do like this. 0x. And I'm actually going to do 0.2x because I know the width of this. And then this will be m.data. Yeah, that seems good. And then we'll do the same thing for data ready. And this is going to be a little different because this is going to be a bool. And here we actually don't want to push to its data because here we're just going to do this. If m.data ready, then we're either going to push 1 here, otherwise we're going to push 0. And so then whenever we do this stuff, we'll just do it whenever we do a clock tick. That's the easy way to do it. I think the other thing we want to do is we'll add a clock here too. That'll be t.signals. We'll do the same thing here. I should definitely put this into a function, but again, we'll just hack this for now, which I think is always a fun way to do it. Clock.wave.push, and then here we need to do p for this particular format. And then yeah, we'll go everywhere where there's this pos edge clock thing here. And we'll do update trace with m. So nm, and then nmute trace. Lol. Nah. wonder if this actually worked. I did want to do this just to make sure there's a new line between signals, but I think this worked. And now if I grab this and I put it into this wavedrom editor, what happens? I should rather open up a new tab for that to make sure I have the other editor instance as a reference that contains valid code. Also, I really should have also added, I'll show you guys what this looks like actually. This is pretty cool. It's a pretty wide diagram. That's fun. But we do actually see data ready comes up here. And it says that data is 80, which is wrong. Also, this is not the best output because you can see it looks like it makes transitions this whole time, which is not really correct. I didn't realize it would do that. So we actually kind of want to dedupe a bit here. And I'm not really sure the best way to do that is. Maybe it makes the most sense to actually push values here and then dedupe on the output, which should be relatively easy here. Not sure. I think that's what I want to do though, actually. So instead of chars here, I don't necessarily want to make this generic, but I might have to. So if we do it over T, no. Let's just be cheeky here. But yeah, I also wanted to actually put in Rx here, which is the one that we're wiggling. But we'll do that in a sec. Let's fix this trace first. I am happy that it worked, but this was not correct. All right, that's because it ran for 1,000 cycles, which, by the way, we know is not going to be correct. So I should actually run it less, which should help us copy this anyway. That'll definitely make it more manageable in any case, but it still is the same thing, just not as wide. So we'll do that now. Actually, we can just do this 20 if we know it's only going to run 16 cycles. I want this to ideally fit in my window, which still doesn't quite, but that's a bit surprising actually, isn't it? Oh yeah, this is 20 additional cycles that it waits at the end. Yeah, 16, 16, and then like 20 here. So it's still going to be a lot, which I guess is fine. I do actually want to put Rx in this before I fix this. And Rx is just one of these booleans as well, so do this. And then this looks like this. So you can see here Rx is initially high and then goes low. And you can see there's our alternating bit pattern, which I believe we have because This is AA. That's the data we decided to test with? Yeah, AA. So there's a start bit, which is this one. And then it should go high, low, high, low. Or I guess low first, because this looks like start bit and the initial period here. And we might already be seeing the issue a little bit here, which is kind of cool. I actually do want to drop this down. No, we'll leave this as is to kind of look at this. So AA again should be, it should have the highest bit set. Oh yeah, we send the lowest bit first. That's why. Yeah, so then 0, 1, 0, 1, 0, 1, 0, 1. Right, which would be all 8. And then around here, we would have expected data ready to happen. But you can see data ready actually ends up being asserted several times. 2, 3, a couple different times. So clearly this is out of sync. But it was in sync when we had a different clock rate and baud combination. So when we went back to 4 and 1, for example, and then in here we need this here. I think I had this at 4. Yeah, I might be writing the test wrong, but we'll see. And here I think it actually ended up working. So here we can see again, there's 4 cycles for our start bit, and then 0, 1, 0, 1, 0, 1, 0, 1. And at the end of this last one, you can see here it responded with data ready, and then we got valid data there. So the receiver appeared to work for at least this single byte. This was really worthwhile to hack this together. I might actually leave it messy like this, even though it bugs me a little. Because again, we get these extra transitions, which I was hoping the tool would help us with. But that's okay. Actually, maybe we do that here. I'm actually going to do that. Let's do this. Let's do last wave entry. Well, I guess actually we can get that from the vector. So let's do this. Function push push P. We'll do that. Let's see. C is P in this case. I guess this push. Well, no, because sometimes we have to push the data. That's why I wanted to have different ones of these. Okay. I'll do push char. So if you want to just push a single one into the wave, it'll follow this path. Otherwise, you can push data. So let's fix that first. I always love hacking together little things like this. Okay, so let's see. We know we want to definitely add it if. So if self.wave.len is, or actually self.wave is empty, or C is different than self.wave.last.unwrap. Like that. Yep. Then what we do here, self.wave.push C. Otherwise, self.wave.push, and then I think we just do a period. and that means the previous value. And now we can do push char. So here we say wave.push p. This can be like this. And this one too, maybe? Actually, this one we don't want to do for data, but for data ready and Rx, we'll do that. And again, that's because this has extra data that we need to check for as well. So now if I load this up, most of these transitions go away, not all of them, which is a bit strange, I think. Oh, because the last one is a period now. Okay, then let's actually use an explicit last value then, which now we can just hide away in here, so that's fine. So last wave char is option. Char. Yeah, that's fine enough, I think. And then here, instead of empty, we could do if self.lastWaveChar is empty, or actually is none, or C is not equal to unwrap. Not the cleanest way to write this, but I think whoop, we need to set it to. This looks better already. There, so now that cleaned up all these waveforms. It did not clean up the data here, which again we expect, so we didn't fix that. And I'm just going to be cheeky here and do this. I'm not writing good Rust here, you guys, and I am okay with it right now. So we'll make push data, which is basically going to be the same. Call this data. This is going to be a string. And here we actually need to do 3 and self dot data dot push data dot clone. I just did last data, didn't I? Last data, fine. Right, so we can do as ref here, which is fine, and I think the comparison will work if we do that. Yep, and now we can push data for this one. Maybe that just works. I think it did. That's cool. So you can see it's actually outputting every 4 cycles. After we do something like this, it thinks there's new data, which is stupid. Or actually, that's not true. This actually looks maybe correct. Yeah, it is. Yeah, because its data changes because it pushes the new bits on here. So that's actually correct that it does that. You can see it RX transitions, and then eventually this is sampled. And I think on the cycle following which it samples, it transitions to this one. So this actually looks correct as it's pushing the individual bits onto that data. And then on the last one, you can see data ready is now high. And it looks good. Man, this was a great way to do this. Very pleased. However, we knew it didn't work when we did this. 16 and 4. Now, first of all, I think I might have actually set up the test wrong because this was 4 and 1, so it's going to send one bit per second, and it thought the clock rate was 4 hertz. If I change this to 16, I actually shouldn't change this, and I should change these to 16. I think is actually more correct. And then this might pass again. It didn't, which I find a little surprising, actually. Because you can see here, it's also changing the data at about the same rate. Not quite. Looks like it's changing it. No, actually, this looks good. And then at the end here, it said, yeah, we're done. And here it says, data valid, and the data was AA. So what didn't work here? $36. So apparently data ready was not true when it finished. I mean, that is the case here. Is it because this happened earlier than we thought? That might be. Which I would find maybe a little strange, but maybe not. As you can see, it does output the right data after it's received that many bits. And it's during the stop bit, which is high, right? This is 0, 1, 0, 1, 0, 1, 0, 1. Maybe this is too early. Because maybe this happens right at the beginning of the stop bit, which wouldn't be correct. So I'm not entirely sure that this is sampling the stop bit correctly. That's my guess. Data ready does not, actually should only be high for one cycle. So it's more that the data just retains whatever value it had, but you can't assume it's correct unless data ready is true. So all we actually need is one single cycle where data ready is high and data is the right value. So here this loop breaks as soon as data is ready, and then we assert again that data was ready, because this loop also might terminate if it gets to the end here. And then if we know data is ready, then we know data is valid, so then we can assert that. So I think that part of the test is correct, but it does actually look like this finishes early. So I'm guessing it's not sampling the stop bit correctly. So I think it's this one. This wait counter. So this has this input bit state, which is what it should be in here. And in fact, actually, would it make sense to check data ready wasn't set before waiting at the end? It should actually, but then I think we'd have to check that every time we bump the clock. So I think a better test would do what you described. In which case it might accept this, but I'm actually not sure that this is valid. So I want to do a couple things here. I want to output some debug stuff for these registers here. So let's do this. m.output. We can do bit counter dot value. And then we can add that here. I'll just do these one by one because it's kind of ugly to do this, but actually it's not too bad. Whoops, I wanted this one here. Whoops. That's what I want. So this is the bit counter. And you can see that this one will count up as it pulls in bits, right? So here it's going to pull in bit 0, and then it transitions to pulling in bit 1. And of course, bit 0 was 0, so that's why data doesn't change here. Pulls in bit 1, 2, and each one of these should last 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 16 cycles, which is what we expect. At a baud rate of 1 with a clock speed of 16 hertz. So this looks correct. You can see again, it's going to sample the third bit, but the current data is 40. So at the end of sampling the third bit, we shift in that bit and we're going to sample the fourth. So that's what that bit counter is going to be. At the end, you can see here, it's sampling the last bit. And once it's sampled the last bit, as soon as it's done that, it says data's ready. But I think this is too early. I think it looks to me like it's not waiting for the stop bit. That's what I'm thinking. I'm thinking it samples this last bit and then it needs to have another wait before this where it samples the stop bit. And that would certainly, if we sent 2 bytes and they both ended with a 0 bit, if we sent 5-5, for example, that would definitely cause this last part to sample 0, and then it might even think it's a new transaction if it doesn't wait for the stop bit correctly. So I think we might have found the problem. But I want to output another debug thing here. We have data and data ready. This wait counter I really want to output. Yeah, the wave drum thing's cool. I mean, it's meant for making diagrams, just to be clear, because I'm a little bit misusing it here. It's made to make like timing diagrams for like documentation, but in this case, it is also functioning perfectly well as a really simple waveform viewer with a really easy to write format. So I'm pretty happy about that. So yeah, this will be this wait counter, and this wait counter is what actually will make it transition between states. We'll put this up here as wait counter. And then I also might want to output the state. Yeah, so now I have this wait counter. You can see it goes from 0, 1, 2, 3. And after 3, that's when it normally samples stuff. And so here you can see it does sample this last bit, which is somewhat after the transition, but that's fine. Yeah, this is clearly not waiting for the stop bit. And I bet as soon as we output our state, that will become clear. And I think actually this wave viewer will support any string for the value. So we can actually decode the state here. And I think we want to do that. So yeah, we have the state value. Oops. So we'll just output the state like this. And then here, I want to put this at the top. And here, we'll do this. Idle. think we can even do this. I hope. So 1 is, what were these states? Idle, start bit, wait. 2 is input bit. And 3 was stop bit, wait. And this should be unreachable. What happened here? Yeah, this actually looks good. This might just work, you guys. Yeah, check that out. Okay, this is actually interesting. It does actually go into this stop bit wait state. So it is actually doing that. It just happens to output data valid earlier, which I think is actually okay. But a little bit unfortunate because that means this looks good. So some interesting things here, which is a lot clearer in this diagram than in the code. You can see it's an idle state until it detects this transition. And I think it does that not long after this. I think this this delay here of a couple cycles, I think, is because of the, well, actually we don't have synchronization stuff here, so I don't actually know why it takes that long to wait for that. Because coming out of idle state, it shouldn't really wait for anything. But this also might be a case of how we have, it might be a case of that we're updating, a symptom that we're updating this trace at the wrong time, actually. Because I think we actually need to do this when we change Rx, for example. I think we actually need to, yeah, I don't think we're quite updating this in the right order, which I don't really care for this test because you can still see things are roughly where they should be. But anyway, what's clear is that once Rx goes low, this will transition into the start bit wait state. And this only counts 2 cycles of this wait counter before transitioning. And the reason is, so normally a bit is 4 of those states. So you can see 0, 1, 2, 3. And that's normally the width of a bit. But as you can see from this diagram I found earlier, and one of the reasons I picked this is because what we actually do is we wait for the start bit. So we go into this in this state, and then we count halfway through the bit, and we sample it again. And this is a robustness feature. So the idea is that if we detect that it goes low, we wait a little bit and see that it's still low, just to make sure we saw a start bit. And if we did, then we can wait 4 cycles each time, and then we'll already be in the middle of all these bits. That's kind of what I was thinking there. And this totally makes sense here. I think also, yeah. Hey, Drew, too. So yeah, so it goes into the start bit wait state. So that's when we're in the bit, and then it waits these 2 periods, 0 and 1. And then it will make sure that it's still low, that it's not a spurious start bit. And then it actually will count 4 of these. And then this will be in roughly the middle of the next bit, which in this case was 0. And that's why it transitions here. So each one of these 4 things here, we're in this, I guess you can't see it because it's over here, but this input bit state. And again, it counts 4 of these wait counter intervals, which again are at this tick interval, which in this case is 4 cycles because that's 16 over 4, I think. Yeah. So yes, we load this bit, and then this next one. It's supposed to sample around the middle. I don't know why this is so delayed off of this Rx signal in this case. That's a bit confusing. I wouldn't worry about it in this case because, again, I think it might be that we have the test set up a little strange for when it actually reads these values. I think. but I'm not entirely sure. Because I don't think any of that's registered here. I think it just reads Rx directly. Oh, it's always on the next tick when it reads Rx. That's why. That's where that delay comes from. So the tick is every 4 cycles. So that's why it transitions here, which is on the next boundary. And again, that should be fine, because as long as our tick rate is four times as fast as our baud rate, then it doesn't actually matter that we're sampling a little bit off here, a little bit delayed. And again, this Rx could actually come in any one of these 4 intervals. So at most we're 4 cycles off, which is, I think in this case, we're like 3 cycles off. So this could only be worse by 1 cycle. Otherwise it'll wrap around and then we'll be exactly on it. So that should be quite safe, I think. Still well within this valid range. So yeah, I mean, this looks good, and then immediately you can see when it starts the stop bit that it's ready. So yeah, Rx is true in this case. This is true at the end. Which might be happening on this same cycle, or maybe the cycle before, I'm not entirely sure. I think maybe we need to propagate here first. That might make it pass, actually. Nope. So it's not on that exact cycle. I wonder actually when that's happening. We definitely hold data high for 16 cycles. It might actually just be that. So I think we set it high. And then we propagate and do 16 cycles. Yeah. So I think it's here that we actually assert the stop bit. Again, a few cycles ahead of this. And there you can see it's already read valid data, because it has. Arguably, we could have this delay until it definitely detects the stop bit, but there's not really any point, I think. I think the more important thing here is that even though this little test that we made fails, which I'll have to clean up later anyway, this actually looks correct, because it did have all the data it needed to report this. And I kind of like the idea of it going back into its idle state kind of as soon as possible. Obviously, it can't do that too early because there's going to be the stop bit. And then, yeah, so our stop bit would have been 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And you can see that this is well in the idle range before it will ever start reading that again. So stop bit should be high for quite a long time during this period, which this to me looks like it's going to be robust. Yet somehow it's not on the actual hardware. I have yet to figure out why. But I definitely know that one thing I was doing wrong is I had this baud rate at 4. And what I didn't do, these actually need to be 4 again. So then the clock is 16 times as fast. I mean, 4 times as fast as the original test. Look, that even passed. Or now the baud rate is 4 times as fast. But everything else, like the clock rate and everything, is the same. So now this weight counter increases every cycle, which is fine. 4 of those is still one of these, because it's, again, 16 hertz and the baud rate is 4 hertz. So yeah. So again here, Rx goes low. We keep it low for 4 cycles. So there's our start bit, and then we have bit 0, 1, 2, 3, 4, 5, 6, and 7. And then right there, And then we would have our stop bit right after that. So again, a better test would definitely catch this and the previous case. And the reason why is because we would normally set up like both a write path and a read path separately. And the write path, its job is just going to write as often as it can, which obviously would be throttled by this protocol. And then the read path would just accept this whenever data was ready, regardless of what the write path was doing. So it would be able to just, every time data came high, it would pull out the data and like put it in FIFO or something, or just read it or check it right away. And then at the end, we would wait until both the write side and the read side are done with their respective jobs. And if both of them are done and the write side wrote all of its data and the read side didn't detect any errors, then we have a passing test. And I might not, I actually want to set that up. I can't words right now. I might actually want to set that up anyway. That kind of fuzzing test. Again, after seeing that this appears to be okay. I'm going to try, just for the sake of trying something, another combination of this. Let's say this was $32. I think we double these then. These become 8. Oops. If it were a 32 hertz clock, and the baud rate were the same, maybe that's wrong. I don't think it is, though. It should be 8, I think. So I actually think this was correct again. Yeah, see, it still produces the right result whenever we make this stuff align. And we would go back down to 4, for example, if this was 8, for example, because it's that ratio that determines this value. This time I got to produce the wrong value, but that might be because I wrote this wrong. I think it is actually, yeah, because this Rx is clearly not changing often enough. Two, 3, 4, 5, 6, 7. Did I just not save this file or something? What the hell? I didn't change the outer loop with the bit count. Oh, whoops. Yeah, good call. Thanks. That's funny. That's why you don't do matching numbers like I did. So just throwing a few kind of clean values at this, it looks like it works. So I might actually have to set up a more proper fuzzing test for this. Just to be cheeky, though, I'm going to actually just try this on the hardware one more time. Maybe it's something stupid. I doubt it, though. I probably just am not catching this with my test yet, but cargo run, and again, to output this to generated.sv. Then we can pull up, oh, whoops, that doesn't work because I have all the Verilog stuff stashed, don't I? Yeah, so I'd have to unstash that. Yeah, I might as well make the test first before I try that again. So I think I'll do that. Thanks for the sub, Dark Second. Really appreciate it. However, I must admit, it was kind of bad timing because I think I'm going to go for today. But I think this was fun, and I'll work on that test, and then we'll get the Verilog output running again, hopefully after we find a bug or don't and think something's off. It might also be that I generated the Verilog wrong, which is possible, but then it's difficult to see, so then I might have to test some simple cases. But anyway, thanks guys for hanging out. Hope to get this fixed soon. But yeah, I'll see you next time.